last class we were discussing about relay drive using a MOSFET. So, we were discussing about what is the use of this diode. In this connection we had shown that if a relay is switched off, then that current that is flowing through the inductor produce a noise spike of this voltage 5000 volt, because when the transistor is switched off, the current flowing through this abruptly stopped. Then this L into dA by dt is induced here, and the induced voltage is 5000 volt, and this 5000 volt is so high that it destroys the transistor. By using this diode, that we are not allowing the current to stop abruptly. So, when this diode is used, whatever current that is flowing is actually returned back through this and it dissipated as a heat, so that the transistor does not see more voltage. If this is 12 volt, then at the maximum this goes only 12.6. that is the use of the diode. Now, next we see other applications of the transistors. Now, this we see for example, we are seeing how to switch the relay using the transistor. Now, we will also we can also use the transistor to switch on and off another transistor with a particular at a particular voltage. For example, this is used as used in power electronics for constant for current limiting. For example, if the current is going very high, then we have to sense the current, and if the current is more than the particular amount, we want to switch off the transistor. For that application also we can use the transistor. For example, we have a resistance, assume some current I is flowing through this. It may be due to transistor or some other device that current is flowing through this. So, the voltage at this point, this ground would be R into I is the voltage that we get across this, and if the voltage is say more than particular amount, we want to activate the transistor. In that case, we have to have a reference, and then we have to have say another transistor to be switched off. Now, this function can be achieved easily using a transistor without reverting back to the operation amplifier. The circuit is like this. For example, if I have a constant current source, then I connect the connect one transistor, and then I will connect this transistor, and connect the base to this. Assume that I connect this current is very small, say 1 milliampere, then I connect this to this. Then assume that another transistor, this is the transistor which is to be switched off. So, I connect this here. Now, this is our maybe it is a relay, or it can be any other load. So, it is immaterial. All that we want is, if this current that is flowing through this, there is current flowing through this is more than particular amount, we want to switch on this transistor, that is our aim. For that we are using this. So, assume that we have a current, say this is a plus supply, and we have a current source, then this we can consider as another load. So, all that needed is, if the current in R is more than particular amount, more than set value, the load R, the load to be switched off. Load, we call it as RL. So, we call it as RL. So, this is RL in fact, this is RL, that is also assume that some connected to plus. So, we name these resistors as R1, this is R2. So, this is transistor T1, this is transistor T2. Now, we see how the transistor is working. Assume that you have at any given point, this is say start with, for example, if this is 0 volt, then this will be at 0.6 volt. Then if this is if I assume that the current flowing through this, the base current is negligible, assume this is negligible current, base current is negligible, base current is negligible. If you assume the base current negligible, then the entire current that is coming here actually goes through the resistance R1. So, voltage across R1 will be so voltage across R1 is equal to the constant current source, which is 1 milliampere into R1. Assume that R1 is equal to 1 K. Then voltage across R1 that is equal to 1 milliampere into 1 K, that is equal to 1 volt. So, if any given time voltage across R1 will be 1 volt. So, this is what we have decided first. So, the voltage across this is fixed as 1 volt, and we know that to switch on the transistor T2 we need base voltage as 0.6, that is we need 0.6 volt at this point to make this switch on. Assume the base current is negligible, that means I can assume that the voltage required at this point is also 0.6 if I want to switch on this. So, the voltage at this collector, so I will put it as this point as A. So, we need voltage required at A to switch on T2 is 0.6. Voltage at A to switch on transistor T2 is equal to 0.6 volt. This is assuming there is no assuming the base current is negligible. So, we need that means voltage at A is to be 0.6 volt, then only the transistor will be on. But if we are taken as this as 0 volt and this automatically comes 0.6, and if this is 0.6, this will be definitely less than 0.6. Because the current, if I assume that all the current is flowing, you need actually 1 volt drop, and that 1 volt is not there right now, because if this voltage comes, if this is 0.6, then automatically some current will flow through this, and voltage across this will not be 1 volt, because what you got is only 0.6. So, in effect the current what is coming is actually going through this, and this current is small compared to this current. So, eventually to tell if this is at if this voltage is at 0.6 and the A is going to be less than 0.6, and the transistor will not be on, that means at 0 volt transistor will not be on. If I want here at A 0.6, then I call this as point B, and the point B must be 1.6 if the current is flowing through this and the current flowing through the base is negligible. Then if the entire 1 milliampere flows through this, and if I take this as 1 K, if this is 1 K, if the entire current flows through this, then if this requirement is 0.6 volt at this point, and then 1 volt across this will go to 1.6 volt. So, that means the base is at 1.6 volt. The base at 1.6 means emitter must be at 1 volt. So, this calls for 1 volt, that means only when the emitter of T2 T1 goes to 1 volt, or the current flowing through this, the current that is flowing through this produce a 1 volt here, then the 1 volt will become 1.6 here, that will become 0.6 here, and transistor will be switched on. Other way around, when the voltage through this when the voltage across this is more than 1 only, the transistor T2 will be on. if it is less than voltage at this point is less than 1 volt, the transistor will not come on. So, effectively speaking that if you write the equation, then we can write voltage at B would be 1 k into 1 milliampere plus 0.6, that will be 1.6 volt. So, you need B should be 1.6 volt. If B is 1.6, then emitter of T21 will be, then emitter of T2, then emitter of T1, sorry, emitter of T1 will be 1 volt. That is only when the voltage across R is 1 volt, voltage across R is 1 volt, the transistor T2 will be on. So, only when the voltage across R is greater than 1 volt, the transistor T2 will be on. So, the transistor acts like a comparator. So, we got switching, that is when if the voltage at this point goes more than 1 volt, this transistor will be on. When the voltage at this point goes less than 1 volt, the transistor will be off. And by doing this, we have done this one particularly for one important advantage, that is this switching voltage. We say now 1 volt is our switching voltage. This 1 volt is independent of the temperature. For example, if I have not done this arrangement, when temperature changes, then the required voltage to switch will change. So, this is a series issue, because if I connect directly the R to T2, then you do not get that benefit. For example, if I connect like this, so you have resistance here and this is R, and if the current is flowing through this, and if I connect directly the transistor here to switch on. Now, at room temperature, what is required, the voltage difference required is 0.6 volt. So, when the voltage at this point is more than 0.6, then this will be on. But if the temperature changes, for example, if the temperature goes up, then the required base emitter voltage decreases 2.2 millivolt per degree C. That means at higher temperature you need only less voltage. That means at lower voltage only it will be switched on. For example, at 100 degree it will switch on roughly around 0.4 volt itself. This problem is not there in the circuit which we have discussed so far, because if you look at the circuit very carefully, what we have done is that we have taken the load current, and then this one is connected to the emitter of the transistor, and the base we are connected through this, and this is connected to a constant current source. Then this one only connected to the switching, the transistor which is to be switched on. So, we had this transistor, and then this is our load RL. So, now if you see, when temperature changes, at room temperature we need to switch on this 0.6 volt, but then at high temperature, when the temperature goes up, we do not need 0.6, for example, we need only 0.4, then assume that you need only 0.4 volt here at high temperature. Then what happened, the switching voltage also this voltage will not change, because this also needs 0.4 only. For example, if this is 0.4, this whatever current that is flowing also will flow through this, and there will be 1 volt, assume this is 1 k, then you need 1 volt drop across this, and this point goes to 1.4 volt, because the current is 1 milliampere. So, 1 milliampere flowing through this produces 1 volt. So, if this switches at 0.4, then automatically this goes to 1.4. Then if it is 1.4, this also, this and this are the this and this at the same temperature. So, this also needs only 0.4 volt difference. That means again if it is more than 1 volt, if it goes more than 1 volt, then this will not be conducting and all the current will be flowing through this, and then this transistor will be switched on. So, you see that even when temperature changes, the switching voltage does not change. This is the greatest advantage of this circuit. So, with temperature, the switching voltage will not change. So, the VBE change in T2 is compensated by VBE change in T1. So, this can be used but the great advantage, because the switching voltage is not changing with temperature. Added to that, if I want switch at different voltages, for example, the switching voltage is taking place at 1 volt, if I want to change the switching voltage, all that I need to do is I change this resistance. For example, if I put 2K, then the switching voltage will go to 2 volt. So, switching voltage also can be easily changed by changing the resistance value. Then second advantage is switching voltage can be changed. Switching voltage can be changed by changing the resistance, R, I think that is kept as R2, that is R1. So, switching voltage can be changed by changing the resistance R1. Resistance R1. So, the transistor can be used easily as a comparator to switch at the required voltage, and that is insensitive to temperature change. Of course, a constant current source needs a reference voltage. Of course, now the switching voltage is with respect to ground, and the constant current source reference need not be at the ground potential. So, this circuit is utilized at many places for switching purpose. Now, we also see some other applications of the transistor, because it is essential to understand the analog circuit properly, how to use the transistor at different situations effectively. Now, let us see how to use a latching function using a transistor. Now, I can take an example from power electronics for this description. So, we next see transistor as a latch. For example, we want switch on the transistor, but then once on, if the load is switched off, then the current will not be there and the transistor should continue to be latched. This kind of application is there in power electronics. For example, if I have a MOSFET switching, for example, power switching is there, then we will have a switching device here, say PWM IC is there, which gives you the PWM pulses to the gate of the MOSFET, and we have a load here, and if the current is more than the level that we like to, more than the level what is allowed, then we want to switch off this PWM, and that should once switched off, it should switch off, should be switched off condition for switch off condition even if this current is not there. For example, once I remove the gate pulse, this current will be 0. But then once current 0, whatever logic that I am using to switch off, that should not again allow the pulse to appear here. So what I do is, for example, I put the switch here. For example, I take this I connect to transistor here, for example, to switch. And if I take, for example, PWM IC say TL494 we have, and this one as a reference output, V reference say 5 volt is available. So I can connect this 5 volt through a transistor, and this can be connected to this. So when the current goes high here, then this transistor will be switched on. Once this transistor on, the whatever emitter current, that will flow through this. Now if the current flows through that, the current will flow through this. Now that will make the current appear here. Now I can make it getting latched. For example, I can put another transistor here, then connect this, then this voltage can be given back to this. So as soon as the voltage goes, as soon as the voltage at this point goes high, say higher than 0.6, then this transistor will be conducting, then the current will flow like this, and that will make the current to flow through this. That means as soon as this voltage goes high, then you will get high voltage here, because this transistor is on first, that will make this transistor on, and then voltage appears here. If the voltage goes high, again this will be on, and that will make this to continuously conducting and make this transistor on, and you will get the voltage at this point. That means now you will get voltage at this point high. Once the current goes high, this voltage will be high, but then once the current goes high, if this voltage goes high, we can give, for example, shutdown terminal of this. So we have a shutdown terminal of this. So this can be given to this. If you give shutdown terminal of this, so this so as soon as current goes high, this will go high, and then the shutdown terminal of this will be pulled high, and then pulses will be terminated. Now to remove to make this transistor to go off again, because the once current goes off, this will be going off, this transistor will be going off, but nevertheless this will not go off, because this already triggered and it caught the voltage here, and this will continue to be conducting, and this will be continues to be high. So the pulse had disappeared, current had disappeared, but then the triggering voltage, that is the voltage which is switched off the controller, still will be there. So when the next pulse comes, we want reset this, because we have to reset, then only the next pulse will appear. Now this is normally done using the provision here. For example, we have a capacitor here. Here you will get a sawtooth wave, and the sawtooth wave is the one which actually triggers the next pulse. So normally what they do is they will connect this to the sawtooth wave here. For example, one can connect instead of grounding it. Instead of grounding it, I can put this, and then I can connect to the sawtooth wave. So when the voltage is high, and when the voltage is high, then there is no problem that there won't be any voltage, because when there is current is low, there won't be any, this won't be conducting, and this voltage also 0, and this is not interfering at all. Once the voltage current goes high, and if this voltage goes more than 0.6, then this transistor conducts, then that current actually goes through this, and that will make this voltage to go high. Then if this voltage is going high, of course, we can limit the current by putting a lower resistance so that it will not disturb this, and once this voltage goes high, this will be shut down. But then once it is shut down, then next then once the voltage had gone high, this will be reset and it will go to 0. At that time, this voltage also will be going through this, and we have to make this voltage drop to 0. That actually can be done by actually removing this. For example, I can connect this diode instead of here. For example, I will put the this diode here. So, I put this. Now, once the voltage at this point drops to 0, this voltage will be dropped to 0 and this transistor will go out of conduction, and this voltage also will disappear. That means, in reality, when the current goes, when the voltage at this point, say I name it as A. So, first step is when voltage goes at A high, when voltage at A greater than 0.6 volt, then T1, T2, then T1 and T2 are switched on. So, T1 and T2 are switched on and we name as T3. So, this we call it as point B. Once T2 is on, then you will get a voltage at point B. So, voltage appears at point B, at B. This switches the, then T3 is switched on. So, effectively when the voltage at A, when the voltage at A goes more than 0.6, T1, T2, T3 all are switched on, and then at B you will get a voltage. So, once the voltage at P appears, then the PWM IC is switched off because we are connected the B to the shutdown terminal. So, effectively when voltage at A goes more than 0.6, so when voltage at A goes more than 0.6, T1, T2 and T3 are on. So, PWM IC is switched off. This makes the voltage at A to disappear, because this once PWM IC goes off. So, you will find PWM IC goes off, then voltage at A disappears. Even voltage at A disappears, it does not matter, since D3 is on, T2 continue to conduct and B will remain there. So, switch off. So, voltage at, so the fourth point is, so voltage at A becomes 0, but T3 will be continuously on. That is, this is the latch function. So, even though the original voltage disappeared, but then T3 will be continuously on and voltage at B will still be there. So, voltage at B, so voltage at B will be present. So, voltage at B will be there even now. Now, but when the sawtooth voltage goes down to 0, that is when voltage at the capacity, I will make it as this is C. When the voltage at C drops to 0, then D3 goes off and then Then the fifth point would be when the voltage at across the capacitor, across the cap C, capacitor C drops to 0, T3 goes off, and voltage at B becomes 0. So, the voltage across the capacitor C drops to 0, then automatically this voltage decreases, and then this transistor stop conducting, and then B this also stop conducting, and B becomes 0, and now the next pulse can appear. So, this way it can act as a latch. That means the pulse once voltage goes high, this can be latched, and the latch function can be easily obtained using this process. Of course, to practically make this circuit work, we need to make a small change, because what happens when this diode is conducting, this needs 0.6 volt. At 0.6 this may still conduct. To make it foolproof, what can be done is I can shift this like this. I can make a change like this, put this and shift this one like this. A small resistance can be added, so that this is 0, this is 0.6, definitely this is not 0.6, and the transistor will not conduct. And also we can use a Schottky diode such that the voltage drop across this is small. So, by doing that we can by using a Schottky diode also we can improve the performance of this. So, you can see the transistor can be used at will for various applications. So, we had shown how to use as a latch in a PWM control IC. We also had shown how to use a transistor to switch off and on at a required voltage, and how to do the temperature compensation for the switching off voltage. That is what we had seen in the first example. And in this example we had shown how to use the transistor as a latch. Now, the transistor also can be used as a temperature compensating element, because when many cases, for example, many transducers, when temperature changes, the property of the transducer changes, and we want to make a temperature compensation. So, we can use the transistor effectively for this, because base emitter voltage of the transistor changes with temperature. That can be used to compensate temperature change of some other transducer. For example, we take some transistor, assume it is changing with the temperature, then how to do the temperature compensation we see in this example. So, how to use the transistor for temperature compensation. For temperature compensation. For temperature compensation in transducers. For example, if you have a transducer, if that property changes with the temperature, how to use this transistor effectively for compensating the temperature drift of the transducer. Assume that I have a transducer here, and then some property is changing. For example, proximity sensor, we have a metal here, and then we have a core kept here, and assume that we have a sensor here, and that is energized, and we have a supply voltage here. This assumes a proximity sensor. So, voltage at this point gives me the displacement. For example, this is the distance we want to see. So, V0. So, voltage V0, which represents displacement D. D is the gap between these two. So, the distance between these two it varies. For example, if this is moved far away, then D increases, then V0 also assume it is increasing. So, assume we have a transistor like this. So, then D is more, then you will get this voltage also more. But then we know that with the temperature this voltage whatever is there will be changing even though D is constant. This is a major problem. For example, V0 is changes, V0 depends on the temperature. So, effectively however V0 changes with temperature of the changes with temperature with the ambient temperature, because this transducer is in the ambient, and whatever the change in ambient temperature that is affects this one. So, even though for a given the distance D is not changing, but voltage V0 will be changing. This is a major challenge in analog circuit. Now, because the temperature drift is a real issue in most of the circuits, particularly the transducers. So, how to make this how to compensate this change. For example, I can sense this change and then do this. For example, one of the application would be driving the sensor with the constant current source. For example, what can be done is I can have a transducer. For example, I put the circuit like this. So, you have a transistor, assume this is supply voltage, and then I have a Zener diode connected this, then I have the resistance here. For example, this is plus 15 volt, and then this is a load. If I take this load can be now transducer, this can be a transducer. Essentially, there is a current that is flowing through this transducer, because this is I, this I is nothing but this is Vz, this is R. So, if this is Vz, we know that this will be Vz plus R plus 0.6, because this is Vz. So, this has to be higher than Vz by 0.6. So, voltage at I call this as point A. So, this is A. So, voltage at point A, voltage at point A is voltage at point A is, assume this is a Zener voltage. Voltage at point A we had find out. So, this is a Zener voltage, assume this is 5 volt. So, this will be the it is not Zener voltage actually, this voltage at this point, say I call it as B. So, voltage at this point will be 15 minus Vz, because this is 15 and voltage across this 5. So, voltage at this point will be 15 minus Vz, that will be 15 minus 5, that will be 10 volt. So, voltage at B will be 10 volt, voltage at A will be 0.5 extra, not Vz, but actually voltage at A would be 10 plus 0.6. 10 plus 0.6 volt, because this is 10. So, this has to be 10 plus 0.6. So, that means voltage at point A will be 10 plus 0.6 volt, that will be 10.6 volt. These are come because voltage at B is equal to 10 volt. That had come 15 minus 5 volt Zener voltage, that become 10 volt. So, we from this circuit we see the voltage at B is at 10 volt and voltage at A is 10.6. So, voltage across this R, voltage across R would be if this is sitting at 15 and this is 10.6, then 15 minus 10.6 is the voltage across R. So, voltage across the resistance R would be across R would be 15 minus 10.6, that will be 4.4 volt. So, we got the voltage across this resistance R as 4.4 volt. So, we know that the base current is negligible, then voltage across this is known, and if I know the resistance value, then I know the current flowing through this. So, assuming R as 1 K, if R is 1 K, if R is equal to 1 K, then current through R would be, that is this resistance. So, we had find out current through this R. So, voltage across is 4.4 and the resistance value is 1 K. So, if I take 1 K, then current through R would be 4.4 milliampere. So, current through R would be 4.4 volt divided by 1 K, that will be 4.4 milliamps. So, effectively it is a constant current source and the current that is flowing through this is 4.4 milliampere, because I had taken this resistance as 1 K. So, voltage across this is 4.4 volt and the resistance value is 1 K. So, current flowing through this is 4.4 milliampere. That current entirely flows through this, assuming the base current is negligible. So, the current I will be effectively 4.4 milliampere. So, current flowing through the transducer is 4.4 milliampere and correspondingly you will have a voltage developed at this point. So, you will have a voltage at this point depends upon this current, and assuming that this has a resistance depending upon the sensor you have and depending upon the displacement D. So, you have a distance D, and because of this variation in D, you will have the resistance of this effectively changes. Since the current is constant, you will have a voltage at this point that will be constant. So, when D changes, effectively when D changes, you will find that voltage at this point is changing. So, the D change will give a voltage change, but then when temperature changes, then this voltage also will change. That was the issue we wanted solved. So, when temperature changes, we do not want this voltage to change. So, only when D changes, this voltage have to change. That is how the transducer is made. So, when D increases, this voltage will increase. The D decreases, this voltage will decrease. But then with the temperature, even for a fixed D, this voltage will be changing. So, we want to compensate that. In this case, that is what happens. When the current which is set here is 4.4 milliampere is constant as long as the temperature of the transistor is constant. If the temperature of the transistor changes, then this current 4.4 milliampere also changes, because when temperature changes, the base emitter voltage is changing and then the available voltage across this is changing, and net result is current flowing through this changing. So, effectively when temperature changes, base emitter voltage changes, that will produce a change in current, and that will compensate the temperature drift of this. This is a method which is used extensively. We will see this now in detail. So, assume the current I is 4.4 milliampere at room temperature. So, the current I is equal to 4.4 milliampere at room temperature. But this current will increase with temperature. I will increase with temperature. That is, temperature means ambient temperature. When ambient temperature changes, this current I also will increase, because when ambient temperature changes, the transistor the temperature of the transistor also changes. So, when temperature of this transistor changes, this current increases. That is because the base emitter voltage decreases with the increase in temperature. So, If we now see at say assume that this 4.4 milliampere is 25 degree ambient temperature, let at 25 degree C, at 25 degree C ambient temperature, see ambient temperature, I is equal to 4.4 milliamps. Now find out what will be the current, what is I at 80 degree C ambient. Now that we can find out by this equation, because the base voltage remains same, because the voltage at B is always 10 volt. So voltage at B is 10 volt. What is this is what we have to calculate. So voltage at B is equal to 10 volt. Then VBE at 100 degree C would be the 25 degree C, we had 0.6 volt minus 2.2 millivolt into delta T, that is equal to 0.6. This is at 25 degree C, 0.6 volt minus 2.2 into 10 power minus 3 into change, that is now we want at 80 degree. So that will be 80 minus 25 degree. So that comes out to be VBE at 100 degree would be 0.6 minus the difference will be 2.2 millivolt. So millivolt into 30 55 degree into 55. So that comes out to be 0.6 minus 2.2 into 55 into 10 power minus 3. That comes 0.6 minus 2.2 into 55, that comes out to be 55 into 2.2, that comes out to be 121 millivolt, that is 0.6 minus 0.12, that will be 0.48 volt. So VBE at 100 degree C would be 0.48 volt. So that makes what is the voltage at point A, because this voltage at B is at 10 volt and voltage at B is 10 volt, and then VBE is 0.48, then A will be 10.48 volt. So voltage at A will be 10.48 volt. So voltage at A would be at A would be 10 plus 0.48 volt, that is 10.48 volt. So at 100 degree C the voltage is 10.48 volt at A, at 25 degree C the voltage was 10.6 volt. So effectively at high temperature the voltage at A had decreased. Now we had find out what is the current flowing through the resistance R1, because now we know voltage across voltage at A. Voltage at A is 10.48. So this is 15. You know voltage at A is 10.48 and this is 15. So the voltage at R is now 15 minus 10.48 and divided by R will give me the new current. So voltage across R we had find out next. So we can find the voltage across R. Voltage across R will be 15 minus 10.48, that will be 4.52 volt. So, you got 4.52 volt across R. So, the new I will be 4.52 divided by 1 K, that will be 4.52 milliampere. So, at 100 degree C the current is 4.52 milliampere. So, current at 100 degree C become 4.52, that means I at 25 degree was 4.4 milliampere, I at 100 degree C 80 degree C is 4.52 milliampere. So, with temperature this current had increased effectively. So, if the current increases, then the current flows through that, voltage across this also will increase. So, in case if this transducer has a negative temperature coefficient, for example, with the temperature the voltage at this point decreasing, means this increasing current will compensate. Assume that this is effectively a resistance, and this resistance, for example, decreases with temperature irrespective of this distance. The distance is remaining constant, but assume this resistance is decreasing with the temperature. It should decrease only due to the resistance, only due to the distance. If the distance increases, effective resistance of this is supposed to decrease, but then this assume that this resistance changes with temperature also. Assume here it is decreasing with temperature, then the voltage at this point will decrease with temperature. Now, the increasing current will compensate that loss. One can select the proper values of R to get whatever compensation required. So, effectively it means this means the increase in current, the current I increases with temperature, So, if this means if the temperature coefficient of the transistor is negative, temperature coefficient of the transducer is negative, meaning with increase in temperature, increase in ambient temperature, voltage across it decreases, across the transducer decreases, voltage across the transducer decreases. That is the meaning of negative temperature coefficient. So, if the temperature coefficient of the transistor is negative, then this arrangement will compensate, because as transducer voltage is decreasing with temperature, but the current applied to the transducer increases with the temperature. So, the decrease will be compensated by the increase in current. So, the one can select the values correctly such that the decrease that you are getting across the transducer is exactly compensated by the increasing current. That is, for example, if I select different values of R, and then if I select, for example, different values of the Zener diode, one can tailor made what is the percentage of current I have to raise for a given temperature change. So, for different combination of this Zener voltage and the value of this resistance, one can get the required rate at which the current has to rise with temperature, and we know if the transducer will drift with a certain amount. If that matches with this, then one can make it the transducer is not changing with the temperature. So, this is another use of the transistor, that is we can use the base emitter voltage change. The base emitter voltage changes with the temperature, that can be used for a positive advantage, that is used as advantage to compensate the temperature change of the transducer and so on. These are very important application. Actually we have constructed constant current source and whose current is not really constant, whose current is really changing with temperature, and that change were used here as an advantage in this circuit. So, in this case the transistor is used, transistor drift is used for our advantage, and this kind of applications are many in the real world, because if transistor is a very dependable temperature drift element, because base emitter voltage changes accurately 2.2 millivolt per degree C. So, this can be utilized at many places for our advantage, because this kind of accuracy you will not get it in thermistor and so on, because earlier they used thermistor as a temperature compensating element, but thermistor also has a good temperature coefficient, in the sense reproducible temperature coefficient, but use of thermistor is not as comfortable as the transistor. So, one can use the transistor for a temperature compensation in very many applications. So, the important property that is used here is VBE of the transistor, VBE of the transistor changes with temperature. And the change is that is 1, and the second point here is VBE delta VBE, that is VBE changes equal to minus 2.2 millivolt per degree C, and this is highly reproducible. With transistor they do not change. The delta VBE, third point is delta VBE is highly reproducible. So, one will get a repeatable result. So, it is possible to get a repeatable result in the mass production, That is why transistor is used extensively for temperature compensation. Compared to the thermistor, transistor used as a temperature compensating element is very common because of this reproducibility. In thermistor also it is possible to get reproducible when the but however the thermistor, if you want a reliable thermistor, you have to pay a lot more money than what you spend for the transistor. So, we see the other applications of the few more applications of the transistor in the next class. With this I will stop this class actually. Thank you.